Hello everybody, welcome back. So today I'm going to continue talking about basic derivative rules, and today I'm going to cover the derivative of e to the x. But the first thing that we need to look at is the definition of e. You ever seen a graph of e to the x power? It looks something like this. So you have a point right here, you have that x equals 1. E to the x is e at x equals 0. E to the x is 1. The graph, as it goes to negative infinity, so the limit of e to x is x approaches negative infinity is 0. So the graph, as we go to negative infinity, approaches 0. So it has a horizontal asymptote at x equals 0. And as we go to positive infinity, the graph approaches infinity. But what is this number e? When we get right down to it, like what is this number? So what this number e is the limit as x approaches 0 of 1 plus x to the 1 over x. So this here is our definition of e. And I'll write it over here as well. And this number e, it's approximately 2.718. So the e itself is a constant number. So this is kind of neat, actually. So you look at this, and 1 over x, as x approaches 0, this approaches infinity. In this, 1 plus x as x approaches 0 approaches 1. So you would think that just 1 to the infinity would be equal to 1. So logically, you would think that this limit should go to 1. But that's actually not the case, which is really interesting. And the reason for that is this isn't exactly 1 raised to the infinity power. Because remember, we're approaching 0, we're not actually at 0. So this is actually a number that's slightly off from 1. So it might be 1.000001 raised to an extremely high power. And this actually comes out to be about 2.718. This limit here. So this is really, really cool. We really need to see. So now, let's say we want to take the derivative of e to the x. So we want dx of e to the x. So this, we know, is the limit as delta x approaches 0 of our function f of x equals e to the x. So when we plug x plus delta x, because this is f of x plus delta x minus f of x all over delta x. So we plug this x plus delta x in for the x in our original equation. So we get that f of x plus delta x is e to the x plus delta x minus e to the x all over delta x. So now if we were to try plugging in 0, direct substitution, we would get e to the x plus 0 is x minus e to the x over 0, which would give us 0 over 0, which is an indeterminate form. And as you could probably have guessed, that this is what we were going to get, but that's not always the case. So always when you're doing a limit, try direct substitution first, and then if that gives you an indeterminate form, continue analyzing. So we have this term here, e to the x plus delta x. Well, we can recall, that if we have the number a raised to the b plus c, for example, this is equal to a to the b times a to the c. And that's, say, for example, you have 2 squared times 2 cubed. 2 squared is 4, 2 cubed is 8, and this gives you 32. You plug in 2 to the 5th. This gives you 32 as well. So just a quick little example. So we can also apply this to e. So if we have e to the b plus c, this is equal to e to the b times e to the c. So if we apply this to this limit, we get the limit is delta x approaches 0 of e to the x times e to the delta x minus e to the x all over delta x. So what we can do now is we can factor out an e to the x. So this becomes limit is delta x approaches 0 of e to the x times e to the delta x minus 1. If we were to distribute this e to the x out, we would end up with e to the x, e to the delta x, minus e to the x, all over delta x. So, now, what we can do is e to the x in terms of this limit, where we're looking for the limit is delta x approaches 0, e to the x can be treated as a constant. So we can move this out to the front. E to the x limit is delta x approaches 0 of e to the delta x minus 1 over delta x. And this is because the reason that we can treat this e to the x as a constant is if I were to draw a graph of e to the x here. Here we have 0.01. And I have my point x here. As we're taking the limit, we're not varying this x. What we're varying is the position of this second point. We're getting this second point closer and closer to this first point. So the delta x is what we're making go to 0, but we're not actually changing the x. And since we're not changing the x in the context of this limit, it can be treated as a constant. Now, in a normal case where you have, like if you're say taking the derivative of like x squared, you can't just say, oh, x squared is a constant, so move it out to the front, and then say this times d dx of 1, which is 0. You can't do this because in this case, x is the variable that you are varying. But in this case, since the limit is with respect to delta x, we can treat the e to the x as a constant. So now it gets kind of odd. We can try direct substitution again. E to the delta x, so e to the x, times e to the delta x, which becomes e to the 0 is 1, minus 1 over 0, which once again gives us 0 over 0. So we need to keep going further. So what we can actually do here is we know that delta x is getting close to 0. So at this point, we're really, really, really close to 0. So e to the delta x is approximately, and remember the limit definition, in this case we're not as precise as if we were taking the limit, but we're around this range. We're maybe 0.01, 0.001. So it's not exactly this 2.718. It's not exactly this limit, but it would be approximately this value here. So e to the delta x would be approximately 1 plus delta x to the 1 over delta x raised to the delta x. In this, since it's an exponent to the exponent, this exponent, the delta x, is multiplied by 1 over delta x. And we know that delta x times 1 over delta x is equal to 1. So this means that e to the delta x is approximately 1 plus delta x for these really, really, really small values of delta x. And if we look at this graphically, e to the delta x, with delta x getting very, very close to 0, we're getting very, very close to 0 on this graph of e to the x. And we know that e to the 0 is equal to 1. So as we get closer and closer to x equals 0 on this graph, e to the x is getting closer and closer and closer to 1. So we can plug this 1 plus delta x into the limit. We get e to the x limit as delta x approaches 0 of 1 plus delta x minus 1, minus 1 comes from right there, over delta x, which is e to the x, limit is delta x approaches 0, the 1 minus 1, this is positive 1 minus 1, these cancel to 0 and leave us with delta x over delta x. And the delta x over delta x cancel to give us 1. We get that this is equal to e to the x times the limit is delta x approaches 0 of 1, which is equal to e to the x. So the really cool result that we get out of this limit here is, and this is our next derivative rule, that the derivative of e to the x is equal to e to the x. So whatever your value for x is on e to the x, say you have e cubed, the slope of the graph of e to the x at the point x equals 3 would be e cubed. So your slope is the same as the value of the graph itself. How cool is that? So let's do a couple of examples. So the first one, and now feel free to pause the video and try to work through these examples yourself. If you have any problems, and then once you're done, like try them out, then keep watching the video. If you have any questions, just leave them down in the comments below. So, first example. Take the derivative of 3e to the x. So we remember from the constant multiple rule that we can bring this 3 out to the front. And this leaves us with 3 times the derivative of e to the x. The derivative of e to the x is e to the x, which gives us 3e to the x. And that was kind of like, okay. Second example. The derivative of e to the x plus x squared. So remember from the sum and difference rules that the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. So this is equal to the derivative of e to the x plus the derivative of x squared. The derivative of e to the x is once again just e to the x plus the derivative of x squared. Remember, we multiply the coefficient by the exponent, so we get 2 times x, and then subtract 1 from the exponent to the 2 minus 1, which is equal to e to the x plus 2x. So now for example 3. Let's say we want to take the derivative of x cubed plus pi e to the x. So this is equal to the derivative of x cubed plus the derivative of pi e to the x. So we use the power rule on x cubed, multiply the coefficient by the exponent, we get 3 times x, and then subtract 1 from the exponent to the 3 minus 1, plus, for this one, we bring the pi out to the front because pi is a constant, and we get pi times the derivative of e to the x. So this first term here is just 3x squared. The second term is plus pi times, and the derivative of e to the x is e to the x. So this is pi times e to the x. So e to the x is, like, it's really just really cool that, like, the derivative, no matter how many derivatives of e to the x you take, like, you're always going to get e to the x. Like, let's say you wanted to differentiate the derivative of e to the x. You would still get e to the x. Like, it changes with itself, if that makes sense. I'm not really explaining that part very well. And to do that better, I'm going to draw our little graph of e to the x again. Here's y. Here is x. And we have e to the x. So what this basically means is, let's say we want the slope of the graph of e to the x at x equals 2. So at x equals 2, y is equal to e to the 2, which is equal to e squared. So the slope of the line at this point would be the derivative of e to the x at x equals 2, which is e to the x evaluated at x equals 2, which is equal to e squared. So the slope of the graph of e to the x at x equals 2 is e squared, which is the same as the y value of the graph. So the slope of the graph at any point on the graph is equal to the graph's y value. So that is the derivative of e to the x. Thank you for watching this video. Tune in next time. I'll talk about the squeeze theorem, a couple of special limits, and then the derivatives of sine and cosine of x. So be sure to tune in for that one. Thank you for watching, and have a great rest of your day.